All right, cool. Okay. So this is great, this graph. We're going to talk about very specifics here in a second. But again, the word is titration. So we've done it in Unit 4. Remember we did the redox titration, where you know it was done because the color changed? Well, first and foremost, that color change has a name, and it's called the transition interval. And some people call it the endpoint. And the reason I mentioned that is last year we encountered a question where it actually said, and the endpoint is this. And a lot of people thought that was the equivalence point. It's not. The transition interval is the point, is the area where a color change happens, but we also call that the end point. For our hydrogen peroxide, it was a point where the purple went away and it turned yellow. That's the end point. Usually the end point and the equivalence point are the same, but not always, as was the case in the question last year. Okay, I'm going to draw a really big curve, and I have a graph up here too, but I just want to walk through it first before I show you the graph. Okay, so yesterday, we talked about how if you're going to graph pH, you're going to start in this beaker, there's going to be a bunch of HA. And let's just make the pH 1. Now, if you have a strong acid and a strong base, diluting your solution by 10 brings the pH up by 1. Diluting it again by 10, bring the pH up another by 1. So 10, 100, 1,000, and so on. But with a weak acid, it's a little bit different, as we found out yesterday. When you dilute something by 10, it doesn't necessarily go up by a full pH point. It's a logarithmic scale, and it's just different for weak acids. Most important, though, we have the equation HA in equilibrium with H plus A minus. And that's what's going on down here. Because this is a weak acid, there's almost no A minus. There's a lot of HA. So far, so good. And then we're going to add, over time or over volume, OH minus. If we use a drop counter, it's actually going to put volume here. If we don't use a drop counter, it's going to put time here. Drop counters are kind of nice, but when they work. Okay, so we're going to add hydroxide. And as we do, the graph is going to start going up. Makes me get a little more logarithmic. It's going to start going up like this. Okay. And then, when you get to this point, which is not the end point, it's the equivalence point, you have only what? We talked about this yesterday.
Only H plus and A minus.
Exactly. Well, the H plus is consumed. Yeah. So the H plus gets consumed, and we only have A minus. So in the beaker, the HA is gone. And again, every time a hydroxide comes in, the hydroxide is going to eat a proton, create a water molecule, and then the HA is going to release another proton and A minus. So as that happens, you go from having all HA to only A minus. At the halfway point, let's just say the halfway point is right here. At the halfway point, our HA concentration is equal to our A minus concentration. And when that happens, the Henderson-Hasselbalch equation is pH equals pKa plus the logarithm of A minus over HA. This is 1. Logarithm of 1 is 0. So at that point, the pH, new red pen, the pH equals the pKa at the halfway point. Okay, so that's what we talked about yesterday. Sound familiar? Okay. After the equivalence point, we're just dumping hydroxides into solution. And the graph does this, and because once again it's logarithmic, and 1 drop of hydroxide brings the pH by 1, 10 drops by 2, 100 drops by 3, 1,000 drops by 4, 10,000 drops by 5, and so on. Okay, so this is the basic area. This is the acidic area, this is the basic area. And at the equivalence point, the Ma equals the Mb, and what's right in the middle? Moles. So the Ma equals the moles of hydronium equals the moles of hydroxide equals moles MbDB. Okay, moles is in the middle. I love that. It's totally the titration stance. So the graph ends up looking like this. Okay. But there's wrinkles. And I want to talk about what happens when you don't have, here we go, when you don't have a strong acid, strong base. When you have a strong acid, weak base, or weak acid, strong base, or something like that. Well, keep in mind, when this is really important, when HA is a strong acid, all of this becomes H plus A minus. What is the acidity or basicity of the A minus? Is it acidic, basic, or neutral?
Basic.
Strong acids form a blank conjugate base. Oh.
Is this one?
Neutral.
Neutral. A strong acid forms a neutral, sometimes negligible, conjugate base. So, actually also, a strong base forms BH plus OH minus, and for a strong base, what is the acidic basicity or neutrality of the BH plus?
Neutral.
Also neutral. Good. So a strong anything makes a neutral. Still wet. A strong anything makes a neutral conjugate. So, talked about this a couple times. Super important. So, strong acids make neutral conjugate bases. Strong bases make neutral conjugate acids. But then we have the weak. So, just to review, a weak acid has the formula HA, not arrow, but double arrow, because in equilibrium, H plus A minus. A weak acid forms what kind of conjugate base? Well, just overall. A weak acid forms a
Strong.
weak base. Okay? A weak acid forms a weak base. And it is true, a more robust weak acid forms a more feeble conjugate weak base. But a weak forms a weak. A strong forms a negligible, a weak forms a weak. In broad strokes, a weak forms a weak. A weak acid forms a weak base forms a weak acid. A strong acid forms a negligible conjugate, a strong base forms a negligible conjugate. So far, so good? And the reason that we can say that a robust weak acid forms a feeble weak base is because the product of the Ka of the acid and the Kb of the conjugate equals a constant. So if the Ka is stronger, or the Ka is larger, the Kb is smaller. But they have to have a Ka and a Kb. And only weaks have a Ka and a Kb. Is that clear? So again, the product of the Ka weak acid and the Kb conjugate weak base is equal to 10 to the negative 14. So if your Ka is very feeble, still a weak though, your Kb is going to be more robust. Or if your Ka is robust, your Kb is going to be feeble. Make sense? This is super important. Strongs make negligible, weaks make weak, robust weak makes feeble weak makes robust weak. The product of the Ka and the Kb is 10 to the negative 14. Now, why is this relevant for titrations? A weak acid forms a weak conjugate base. Base. I don't know what I said. Where's my finger? Base. Okay? So, let's take this titration curve. I want to bring up that here. No, it was actually right here. If we react a strong acid to strong base, the equivalence point will be 7. It will be 7. Listen carefully. Because the conjugate of the strong acid is a negligible base. And a conjugate of a strong base is a negligible acid. So both the strong acid and the strong base make 2 negligible conjugates, so the equivalence point is 7. So after the titration happens, the leftovers have no effect on acid-base, acidity or basicity. Now that changes when you have a weak in there. If you react a strong acid with a weak base, the equivalence point is no longer at 7. The strong acid will form a negligible base, but the weak base will form a weak acid. So the pieces that are left over after the titration, the strong acid leaves behind a negligible base, and the weak base leaves behind a weak acid. So if a strong base reacts with a strong acid reacts with a weak base, the equivalence point will be acidic because there's an acid left behind.
So less than 7.
Less than 7. Yep. This is not an excellent diagram. This one's better. And then, of course, the opposite's also true. If a weak acid, which is usually what happens, if a weak acid reacts with a strong base, the weak acid leaves behind a weak base. The strong base leaves behind a negligible acid. So when a weak acid is titrated with a strong base, which is usually what we do, it's what we're going to do next week. Next week? Yeah, next week. Because we have ACPs, 8 APCs tomorrow. Then what is left behind is a weak base and a negligible. When this happens, the titration point will be basic. It will be basic because the weak acid left behind a weak base. The strong base did not leave behind an acid. Its conjugate acid is negligible.
So strong and weak are both 7.
No. Strong is 7. Weak depends on the Kas. So I'm going to draw a little table here in a second. So does the general idea, does it resonate with you? Strong, nothing's left behind that changes anything. Weak, strong, the weak things leave something else that's weak behind. Okay, so let's bring up I'm going to draw this. I draw this right here. So weak acid, strong base, pH is going to be more than 7. Weak acid, weak base, and it depends on the species, and we're going to talk about that. Okay, there's our graph. It's a good graph. And I don't use the watery eraser. Is this eraser better? A bit. Is this eraser better? Not really. Okay, make a table. I love making tables. So everything I put on here is right there. Yeah. Okay, so here's our table. Okay. We're going to start, so the acid and the base, the conjugate acid, conjugate base, and then the result. If our acid, let's make lines. Lines are fun. If the acid is strong, and the base is strong, the conjugate acid is going to be
Neutral.
Or be neutral.
negligible or neutral, and the conjugate base is going to be
Neutral.
neutral. And the result will be a pH of 7. Yeah? Are we cool with this? If the acid is strong and the base is weak, then the conjugate acid will be weak, and the conjugate base will be negligible, and the pH will be
Lower than 7.
less than 7. Great. If the acid is weak and the base is strong, then the conjugate acid is going to be negligible, the conjugate base is going to be weak, and the pH will be greater than 7. Now this is where things get interesting. If the acid is weak and the base is weak, then you have to look at the Ka and the Kb. Okay? So the Ka times the Kb will equal 10 to the negative 14. So if your acid's Ka is 10 to the negative 5, then the conjugate base's Kb is 10 to the negative 9. Huh? Use a different color. If the weak base's Kb is 10 to the negative, let's make it interesting, 10 to the negative 3, then the conjugate acid's Ka is 10 to the negative 11. So you asked, is it going to be the same as strong? No, because you have to look at what's left over. Which of this is bigger, the Ka or the Kb? Kb. So then the pH in this case, the pH in this case, bigger than 7 or smaller than 7?
Greater than 7.
Greater than 7, it's basic. Because the Ka of the conjugate is a weak base than the Kb of the conjugate is a more robust weak base. Is that clear? Cool, because everything else is just math. Questions? I worked really hard on this graph, so again, here, all HA, here, all A minus, at the equivalence point. Can't draw this enough because I don't know why it showed up, but it did. End point, color change. Equivalence point, mole. Halfway between, HA is A minus, which means the ratio of HA to A minus is 1, logarithm of 1 is 0. Henderson-Hausbach says the pH is going to equal to pKa. Okay. Questions so far? If you're comfortable with this, give me a thumbs up. Hank, I'm hoping you get this. Not ask questions. Okay. So they do things like, what is the major species, or what is the species with the greatest concentration? You saw this in the previous exercise set. So what's going on here, and this is the classic one that AP loves to use, and we're going to talk about, we're going to use next week, is we're going to take some acetic acid. The acetic acid is going to be titrated with sodium hydroxide. Weak acid, strong base. And then that's going to leave behind water and sodium acetate. Okay, so far? So at the end where we find an equivalence point, the pH is going to be acidic or basic? Basic. And it is. It's up here near 8. That's the equivalence point right here. So this is the first half of the curve. This is not the whole curve. This is the HA. This is the A minus. And in between, the sodium acetate, or the acetate ion, is equal to the acetic acid. So you look at this and say, okay, before the reaction begins, which thing has the greatest concentration? Acetic acid or acetate ion? Acetic acid, because in weak acid, it's almost all undissociated molecules. You get to the half equivalent, so he says equivalence. Sometimes they do this too. Instead of giving you volume, they'd be like a whole half. Anyway, so at half equivalence, they are equal. The acetate ion and the acetic acid are equal. At the full equivalence point, the acetate ion is completely replaced, has completely replaced the acetic acid. Then everything after that is just dumping hydroxide into solution. All right, questions? Okay. Well, the equivalence point is integers how do the following change? Okay, so this is the last step. Now that we reach the equivalence point here, and we keep adding hydroxide, how does the sodium change in solution? We're going to keep adding sodium hydroxide. How does the sodium change, sodium concentration?
It increases.
It increases, because you are literally dumping sodium hydroxide into solution, and the sodium has nothing to react with. What about the hydroxide? What does the hydroxide do after the equivalence point? It increases, because you're dumping hydroxide into solution, and it has nothing else to react with. It has already eaten all the HAs. What does H plus do? Decreases, exactly, because of the 10 to the negative 14, if hydroxide concentration increases, the hydronium concentration has to decrease. It's still a water solution. Even though all the HA has been eaten, there's still protons in there in the form of water molecules. So when you add hydroxide, that's going to go up, and the water is going to give off protons, and that's going to go down after the equivalence point. Does that make sense? Okay, because you're like, well, their action's done. There's nothing else to go on because everything was consumed. No, because there's still water molecules on there. There's still H pluses and A minuses. By dumping OH in there, you're going to consume some of the H plus. Because no matter where you are, the concentration of OH minus times the concentration of H plus must equal 10 to the negative 14. Everywhere, all the time, as long as you're at 298 Kelvin. Okay. And then finally, what happens to the acetate concentration after the equivalence point? You keep dumping sodium hydroxide in.
Stays the same.
Yeah, no change. You've basically created as much as you can, and you're not going to get any more. I think that is everything. Yeah, it's just logarithms. So here, this is nitric acid, a strong acid, sodium hydroxide, a strong base. So as you add it, there's going to be a concentration of sodium hydroxide. The H plus is going to go down, the hydroxide is going to go up, and the sodium will go up linearly. Okay, keep in mind, because you have two products, hydroxide and hydronium, their product equals a constant, so they do not go up linearly. Do you realize this? This is just a math thing. Let me draw it this way. If the product of y times x is a constant, which it is, this is going to be, let's just arbitrarily make this H plus, arbitrarily make this OH minus, and that's 10 to the negative 14. So the product of two things is a constant. When one increases and the other decreases, they do not increase and decrease linearly. They both decrease 1 over x. So they do that. They do not rise or fall linearly. Is it going to be on the AP? Maybe. Probably not, but maybe. You might someday have to pick out the graph. It might be a multiple choice question. It might even be a free response question worth 1 or 2 points. Pick the graph for the change. Well, it's not going to be a straight line because the product of that and that must equal each other. So if one goes up, one goes down, they have to basically be graphed 1 over x. All right. Okay, weak acid, same deal. Hydroxide still got to be that. Hydrogen is going to be that. This H, A, oh, HF. Yeah. So HF eventually gets entirely consumed. We talk about the Henderson-Hasselbalch. How comfortable are you with the Henderson-Hasselbalch equation? Basically, you understand what it means, okay, because of the math we did yesterday. Basic buffer. Hey, you can do the Henderson-Hasselbalch for bases also. A basic buffer is what you would make if you had a base and its conjugate acid. To make a buffer, the phrase that the AP wants to use is acid with its conjugate base. To make a basic buffer, base with its conjugate acid. We're gonna do this next week. I think that's gonna be, I don't know. Two of the labs are next week and one of the labs after spring break. Okay, so what do you think would happen to the Henderson-Hasselbalch if you wanted to make the Henderson-Hasselbalch for bases? How would you write it?
pH equals PKB.
Wouldn't it be PO?
Yeah.
pH.
Yep.
So we would write
PKB.
P.
It's not blue.
Let's try yellow. We go POH equals PKB plus log of BH, BH plus concentration over B, which you can totally do. This is on your formula chart. This isn't, but you could use it. Works exactly the same way. Yeah. I think that checks all the boxes for everything we need to do for acid base. The only thing, blood buffers. We don't really do, blood buffers aren't in the AP anymore. But it's kind of fun to know what a blood buffer is. When you bring oxygen and carbon dioxide into your blood, your pH drops because it makes carbonic acid. And when you eat and you put minerals into your blood, your pH rises. To keep it from rising or dropping too much, you have buffers. Buffers basically do exactly what you think they do. Like when you download something and it streams, you basically collect an extra couple megabytes of information. So in case a bird flies over your satellite dish, you still get your consistent video. So buffers work the same way. This is how they work. When you add an acid into a buffered solution, it takes the proton and creates something that doesn't change acidity. When you add a base, the buffer releases a proton and creates something that doesn't change acidity. Yeah, there's a whole unit on buffers, which we're going to do sometime next week. pH solubility, moved buffers, and Wednesday next week. Oh, oxo acids, ick. Okay, that's it. Oh, one last thing. What happens to the acid-base KW equilibrium at a higher temperature?
It changes.
It does, but how does it change?
We got a 50-50 here.
Exactly, yes, you exactly do. You totally have a 50-50 chance here.
It increases.
10 to the negative 14, which is a concentration of H plus. Oops, that's supposed to be a bracket. Concentration of H plus, again, if you like to write H3O plus, that's fine too, times hydroxide. And the equation is you have an H plus a hydroxide, and they're in equilibrium with H2O. I believe it's just about done. Okay, and yes, the answer is it increases. KW. I have to draw this backwards. It's been that kind of morning. I want to make sure. I want to make sure I'm throwing an actual number at you. Okay, KW at
Our temperature.
300 Kelvin.
Oh yeah, I say it increases.
Yes.
Seems like a move around.
Well, that doesn't help.
That's just my explanation.
Okay, AI is wrong. They're like, the KW is 1.1 times 10 to the negative 14. It's like, no, it's not. It's maybe 500 Kelvin. Does it still get it? Nope. Okay. Oh, it's still doing it. Oh my gosh. Okay, so AI sucks. It says the
Is it Gemini?
at 500 degrees, yeah, Gemini. At 500 degrees, the KW is 1.0 times to the negative 14.
ChatGPT.
Yeah. Yep. I can't give you a number. We'll just have to pretend to make. We're just have to make one up. Yeah, see if ChatGPT.
It says 10 to the negative 12.
Oh, that's way too big. It's totally not that.
Um,
It's not going to change. It's not going to change by 100. It's going to change by like 10 at most.
if you increase the temperature that much, could it change? It says a high. I don't know. It says increases significantly. I don't know.
Maybe I'm wrong. Maybe it does increase that significantly. Okay, let's just make it something else. Let's make it something real easy. Let's make it. Look, we're going to basically. Okay. Let's pretend that the KW at 400 Kelvin, so 123 degrees warm. Actually, let's keep them liquid. Let's make it 350 so it doesn't boil off. The KW at 350 Kelvin, let's pretend it is 1 times 10 to the negative 13. Understand that 1 to the negative 13 is larger than 10 to the negative 14?
Yep.
Okay. So that means if it's a neutral solution, the H plus concentration is still equal to the hydroxide concentration, and that is equal to what?
Negative 6.5.
Can we accept that negative 6.5 is larger than negative 7?
Yeah.
Okay, here's where it gets really strange. If that is the case, what happens to the pH range?
It's from 1 to 13. Or 0.
Yes.
Because it is, when you look at ions, you're basically saying there is now more ions in solution at a higher temperature, which means the product is still some number. In this case, the product is going to be 10 to the negative 13. The sum is still going to be 13, but if there's more ions, that means the whole pH range broadens. So instead of going negative 1 to 15, maybe it's negative 1.5 to 15.5, because there are simply more ions in solution. Okay, that's way beyond the scope of this course. All that you need to know is when temperature changes, so does KW. All that's ever been tested. And the question is usually something to the effect of, it'll be like, we found the pH of the neutral solution to be 6.3 at a neutral solution. Explain. That's usually the question. It's almost always that form. And you're like, well, because you're not at the normal temperature. You are not at 273 or 298 Kelvin. Since you're not at 298 Kelvin, the KW increases, and 6.3 times 2 means your KW would be 1 times 10 to the negative 12.6. Is that right? Yeah. Does that make sense? That's the question that always shows up. Nothing else besides that. The math is just trivial. Okay. With the rest of the time we have, let's do some math. Boop. Make sure I talked all the boxes. Yep. Again, endpoint. Color signal the arrival. Endpoint. Why they call it the endpoint, nobody knows. The equivalence point is when they are equivalent. Yep. We talked about titrations and titrations. Strong acid, 100% ionization. Do you understand the percent ionization? Because you weren't here when we talked about that.
It's what, how many moles, like, are ionized versus the moles of particles here, overall?
Concentration.
Oh, yeah.
Yeah, it's the concentration of the.
Yeah.
If they're in the same volume, then they will have the same molar ratio too. But yeah, it's the concentration of the A minus over the HA. Looking for something interesting to do. Sodium hydrochloride, sodium chloride, find the concentration. This is just limiting reactant. You guys remember how to do that? Find the moles, find one being reacted. Okay. There's got to be something more interesting in here. By hydrox. Oh, KHP. Okay, here's another word. Standardized. Liquids are very hard to get exactly right. We'll be lucky to get tenths of a milliliter. But mass is very easy to get right. We can go down to like the 10,000th of a gram pretty easily. Because of that, a standardized solution is one that is tested in titration against a solid acid or base. Okay. Standardized basically means you've got its concentration very precisely because you titrated it against a solid, which we're going to use. The classic solid is called KHP, potassium hydrogen phthalate. Yeah. Make sure you're not standing next to somebody aiming at them when you say phthalate. Okay. Yeah. This is all just MAVA equals MBVB. Come on, give me something. Ooh, here we go. Yep. Determine the volume that must reach the equivalence point. That's more of MAVB. The pH of the half equivalence point, and then the pK. Okay, so this is what we want to use. Okay, so let's do this one. A 3.0. Oh, you know what? That's probably 3.0 molar. Well,
Oh yeah, it's gotta be.
let's just go ahead and make it. Let's just pretend it wants 30 milliliters.
They couldn't write 30.
It's almost certainly a typo. Let's just pretend it says 30. So we're going to have we're going to do a titration, and in this titration, we're going to begin with 30 milliliters of what molar?
0.5.
0.50 molar, and the acid is acetic. Okay, HC2, C2H3, H3O2. You weren't here, Canyon, when we talked about the 3 ways to write acetic acid at the end of the last video. Some people write it this way, C2H3O2. That's the way I write it because it puts the proton in the front. Some people still want to torture kids, and they write it like that, CH3COOH. And some people are just devilish, and they write it this way. It's all acetic acid. The reason they do this is acetic acid looks like this. It's called a carboxylic acid, it's a weak acid. So they're like, oh, I'm going to draw it like that. And some people are like, I hate kids, I'm going to draw it that way. And I'm like, I think this is best. So there we go. Okay, so and we're going to a sample of 0.5 molar. So we're going to add to it 0.50 molar NaOH. And the question is, how much do we need to use? So to determine the volume of sodium hydroxide must be delivered to reach half the equivalence point. So if you're ever asked, how much do you have to use to get half the equivalence point, you should calculate how much you had to get to the full equivalence point, and then half it. And again, the graph is going to look like this. Whee! Where's the equivalence? Approximately, where's the equivalence point going to be? What number? Give me a number. It is a weak acid and strong base. Strong base is going to be what kind of conjugate?
It's going to be greater than 7 because you have a weak acid.
Yep. So I'm just going to, I know it's about 9. And the reason it's 9 is because you had a strong base made a negligible conjugate acid, and a weak acid made a basic conjugate base. So about 9. All right, so we'll just do math. Take your calculator, find out what the volume is of the actual equivalence point, then just half it.
Isn't that called the perfect buffer, or is that
Yeah.
a different thing?
The perfect buffer is when the pH equals the pKa. Yay! That's what makes it easy. Yeah, if you do any math at all, part B, you're doing it wrong.
Oh my god. Oh, it's
So, but part A, do the math for part A. But if you do any math at part B, you're doing it wrong. Understand why? Because it wants to know what the pH is at half the equivalence point. It's that, or pKa equals the pH. Because half the equivalence point, the bottom half or the back half of the Henderson-Haas-Block disappears. But let's go ahead and find out what it is. What is the volume at the equivalence point? So what is the volume at half the equivalence point? You guys done, hopefully? So if it's 0.5 molar acid and 0.5 molar base, and you added 30 milliliters of acid, how much base did you have to add? 30 milliliters. So 30 milliliters would have to be where you get to the actual equivalence point, where you got a whole bunch of A minus. You start with a whole bunch of HA. So how much would it be at the half point? That's not that complicated. It's 15 milliliters. Okay. And this is where the HA concentration equals the A minus concentration. And again, at the half equivalence point, the bottom half of the Henderson-Haas-Block disappears and the pH equals pKa. Identify the main species that are present in the solution being titrated at half the equivalence point. I don't know what they mean by main species, but I do know what they mean by being titrated. The being titrated is the HA. The HA is being titrated with hydroxide. So the HA is reacting with the hydroxide to produce the H plus with the hydroxide reacted with it. I don't know what they mean by this, but the important thing is, that's the important thing. Start with HA, end with A minus, hydroxide comes in, eats a proton, HA releases a new proton, and we're all happy until we get to the equivalence point, at which point there's no more protons to eat. Yes?
I thought you said at the half equivalence point, the concentration of H3O equals the concentration of OH.
No. The concentration of H3O times the concentration of OH will always be 10 to the negative 14. And the only time it will be equal to each other is in a neutral solution, which we cannot have with a conjugate weak base.
So that at equivalence, the concentration of OH equals the concentration of the acid.
Oh,
Or wait,
I see what you're asking.
I'm confused.
Yes, okay, I see what you're asking, yes. So if it is a neutral solution, is the concentration of the hydroxide equal to the concentration of the hydronium?
Yeah.
That only happens at pH 7. So the equivalence point is not that. It's not H plus equal OH minus at the equivalence point. The only time that ever happens is when you're at pH 7. Does that make sense?
Yeah.
So it's like, yeah, the equivalence point is not a neutral solution. Good question. Others? We're just about done for the day. Ooh, I made it tiny small. Okay, so more math. There's that. So this is fun. Again, we talked about this. It's equal. What you're going to be doing after spring break is I'm going to say, here's an acid. It's going to be a solid. Make me a solution with pH of that. And you're going to do the math. It's actually kind of cool. Yep. Okay. Yep. We did that a whole bunch. All right. And let's end with talking about polyproducts. Polyproduct curves are interesting because they have 3 equivalent points, or 2. And we used to use a polyprotic acid called citric acid. I think we still do use citric acid. Citric acid is H3. So I'm just going to say H3A When you have a polyprotic acid, like phosphoric acid or citric acid, yeah, citric acid is polyprotic or citric or phosphoric or citric, you only use one proton, and then the anion is H2A minus. That is one equivalence point.
That's 310.
The second equivalence point is another proton reacting and leaving behind another O2 minus, another conjugate. The third one could technically exist, but you almost never see it, and I will try to draw why. So again, and then this would just become a plus a 3 minus. Alexa, stop. A polyprotic curve looks like this. Big curve for the first proton. Smaller curve for the second proton. Itty bitty curve for the third proton. Okay. So much that we almost never see that third curve. Sometimes we see the second curve. But there's one more thing that we can pull from this. Because of this becoming smaller and because of the conjugate becoming a stronger and stronger base, because the acid is becoming a weak base or weak acid. Let me say it again. Because the weak acid is becoming less and less robust, its conjugate base is becoming more and more robust. So, if you were to graph all these points, let's pretend we're reacting against hydroxide again. This first one would probably be about 8. The second one would probably be about 10. And the third one would probably be about 12. Because, again, these numbers probably not quite right, probably 8, 9, 10, but you get the idea. Because your acid is becoming less and less robust, so your conjugate base is becoming more and more robust as you go through the procedure. This has never been on the AP. But it's in the curriculum, so here we are. All right, ready to call it a day? Questions before we turn off the video and say bye-bye to Hank?
Okay.
Bye-bye, Hank.